Hello, my name is Nur Ahmed, and today in this video we are going to generate that time for PWM signal. So in our last video we generated PWM and we changed the duty cycle and we simulated. So in this video, according to that PWM signal, we are going to generate a complementary two PWM signals with the dead time. So in a half-bridge topology, this PWM signal needs to generate a complementary PWM signals with dead time in order to avoid shoot-through current on the half-bridge topology. So this dead time generation actually is very simple as if we think about it, just the edge delay. So this is we have a original PWM signal, and for the high side we delay this edge for a little bit time and then turn on this and then follow this original PWM. And for the low side, it's gonna invert this edge. And for the low side, when this one is turned off, then it's gonna delay this edge, turning off edge, delay for a bit time, and then turn on. So this is basically a edge delay. So we can write a edge delay code in VHDL. Uh, uh, just generate one block edge delay, and then we instantiate this block for the another PWM for the low side. But for the low side, it's gonna for the falling edge. It's gonna for the falling edge delay. So let's start in our VHDL. So first, we created a project named Deadtime Gen, and then inside this one, we first write a code about PWM edge delay. So we have three inputs. Two inputs as a clock and the PWM in, and then for the PWM output is the delayed edge version of this PWM in. So architecture of this PWM edge delay is before we begin, we are going to define a constant, which is the dead time. This is gonna be constant. Oh yeah, before that, let me add some library here because we are going to use some numeric. So we have numeric tt all, and also we are going to include this unsigned. Sorry, there's a dot here. The logic unsigned all, right? We are going to define a constant, a value. It's that time, but since we counting the clock cycles, so let me just name this one as that cycles. This is a constant, and the type is integer. Let's start with let's say the dead time is 5 clock cycles, and then we are going to define what? Define a counter. So this counter will this is the delay counter. This is going to count how many cycles for the dead time. This is the vector based. We don't need too much cycles, so just a 4-bit counter is enough. So the maximum clock cycles is 16. So here, this one is that time. We can adjust this, adjust that time here, and this is the counter. So the maximum dead time should be 16 clock cycles. All right, and then let's sorry, this one is begin is here. All right, begin. So process clock begin. So we're going to detect that edge. So if at the rising edge clock, then first we're going to look at the input signal. If it is 0, then we just assign PWM output as logic 0, right? So if you look at here, if PWM input is low, so we just need to, right now we are creating edge delay for the high side. So if it is low, we don't need to do anything, so it's gonna low. After it's 1, then we need to delay the edge. So if it is 0, then we want to make sure that this counter is reset to 0. Okay, if PWM in, else, which means if PWM in is not 0, and also if the counter delay is smaller than, so this counter counting, but it is still smaller than this value, I'm gonna here subtract 1, just 1 clock cycle smaller than this, whatever we define here. In that case, then we need to continue to, so the counter still needs to continue to count. Else, so that means here PWM in is already 1, and also else here the counter is already count to this value, that cycle value. Then in that moment we're gonna assign PWM out as 1. So this gonna delay this amount value, then we assign 1 to PWM output. So here and if, and here we have and if, this and if for this version, and then here and process. Okay, mismatch process expecting if what did I miss here? If rising edge. Oh, sorry, we have another and if here. So and if for this one, and if is for this one, and for the if rising edge clock we have another and if. Let me just log format. Okay. All right, so we created the edge delay for this side. So if PWM in is 0, this one is going to 0. Else PWM in 1, then we start to count. In the previous time, the clock the counter we always reset it to 0. At this moment, the counters start counting from 0 until that time that we set it there. And then once it's finished here, and then the PWM output is high. Okay, so we delayed here. So this on the falling edge, no need to delay for the high side. Now for the low side, we are going to delay the other side, falling edge. So we can do it on the higher level. So on the higher level, which means we have that time generation block, and it has this one input. It has two outputs, and PWM output for this one just take the PWM edge delay this code, and then we instantiate this code, but we invert it so that it's gonna delay for the falling edge. So let's create a source. Let's name this one as Deadtime Gen. As for the input, I'm going to name this PWM int for the Deadtime block to differentiate from the PWM input from previous block. And we have two outputs, so I'm going to name it for the high side out, and PWM output for the low side out, and also we have clock for as an input. So I'm going to copy this library. Space is here. So our entity is Deadtime Gen. We have one PWM input and the two PWM output as complementary signal, and we also have clock. So for here, we need to call that PWM edge delay. So component PWM edge. Sorry, this calling should be before the begin. Component PWM edge delay is for the ports. Actually, we just need to copy this one entity, right? So we just copy entity, paste it here, and change the name entity to component, and then and component. So we have PWM in, PWM out, and we call this function, and then we need to instantiate this function. For instantiation, we need to call instantiate 2 times, one for the high side, one for the low side. But before that, we are going to define one internal signal, which is we need to invert that PWM input for the low side. This is going to be std logic. So this one is internal signal for the low side. You need to instantiate 2 times, for the one for the high side, PWM edge delay, and port map is So what are the port maps? So we have this PWM in assigned to this PWM in that time. PWM out. PWM out from the edge delay goes to our high side, and clock as usual goes to clock. Alright, so this is for the high side, and for the low side we just need to copy. Let me copy, just copy paste this one. We instantiate this one as a low side and the port map here. So PWM in here need to take the inverted version. So we define internal signal as not PWM in here, because for the low side we need to invert that PWM input signal. And then PWM output from the edge delay, because we already inverted, it can goes to now low side, and the clock goes to low side. Now here we still didn't define what is not. We already defined this clock not PWM in, but what is not PWM in? This not PWM in is not the logic relation of whatever goes to this block. Whatever the signal goes to this PWM input that time, it's gonna invert this one assigned to this not PWM in. So we inverted. So in that case, the PWM edge delay will be it's gonna work on the falling edge. We inverted, so the edge delay will work on this on the falling edge. All right, so now we created that time generation block. So our top level is that time, and then we have these two instantiation, two sub blocks for the high side and the low side. Now, how do we validate this PWM generation, this code? So we need to combine with our PWM generation from the previous video. Let me just hit here. We are going to generate a top level, which is whatever inside these broken lines. This is on the top level. This PWM gen block we generated from our previous video. It has clock and reset as input, PWM out as output. So we're gonna take this output fed to this Deadtime generation block, and then we're gonna generate these complementary PWM output, two PWM output signals. So let's generate this on the top level. So in that case, I'm going to again create one file and name as top level. Finish. So this top level, what are the ports? So we have two input ports, which is clock and the reset, and the two output ports, two PWM signals. So let me name clock as the input, reset as the input, PWM out 1 as the output, and PWM out 2 as the output. Once we generated this block, we already have these two blocks. We just need to call these functions and instantiate these two sub blocks. On the top level, let me again copy these libraries. All right, so we have these entity ports and architecture. Here, before begin, we need to define one internal signal here. So we have this one internal signal, which is from PWM gen block to Deadtime gen block. We need to define this internal signal. Let me define this internal signal, name it as PWM out, because we already have this PWM generation block out. Let me just name it as internal because this is internal signal. STD logic. So this is the internal signal. All right, so we need to call those functions. We just need to copy paste from the entity for the component, right? So we need to add that PWM gen because this top level will include that PWM gen block. So let me add that file. That one is PWM gen from our previous video. It's gonna sources, new PWM gen. I'm gonna copy source into the project. Finish. Alright, so we have this PWM generation from our previous video. This one have PWM gen out signal. So we need to call this function, which is we just copy this entity to here, and then change entity to component here and component. So it's gonna generate PWM for this for our Deadtime block, and then we have another block Deadtime gen. Just copy paste this component. Okay, now we can begin. Now we need to instantiate these two blocks. So let me just name as PWM gen inst. It's gonna be PWM gen. In terms of this PWM gen, we have 3 ports: clock, reset, PWM on. So clock goes to top level clock, and from this reset goes to this top level reset. Now this PWM gen out, this output from our PWM generation block, will go to this signal, internal signal. So internal signal we defined here. Okay, close it. We called the PWM gen. Now let's call the Deadtime gen. Deadtime gen, let's call it instead, and then Deadtime gen. The port map is, what are the ports for Deadtime gen? PWM in, Deadtime. So this one this one will coming from this internal signal, right? So whatever goes to this PWM in Deadtime block is coming from this internal signal. So we just copy this internal signal here. clock goes to clock. And what else we have here? So for the high side, inside our Deadtime block, the output is PWM high side, but on the we can name it as actually the same, but I just want to differentiate in different hierarchical level. So here Deadtime gen output is PWM high side, PWM low side, but on the top level I name it them as PWM out 1 and the PWM out 2. So PWM high side goes to PWM out 1, PWM low side signal goes to PWM out 2. Okay, that's it. Save it. Hopefully there's no error. Okay, no error. So we have top level now. Inside top level we have PWM gen block and Deadtime gen block. Inside that gen block we have PWM edge block. All right, so we need to simulate this one to have a look if our code works or not. Let's add source create simulation. I'm gonna create in Verilog and name it as top level test bench. Okay. Finish. Let me just finish it here. So if you seen the first video PWM generation, we had clock. We define the clock period as 5 nanosecond. 5 nanosecond. So for the timing scale here, we can just use the 1 nanosecond as a one-time unit. And this one, let me just put it as 100 picosecond. Okay, so we don't have any ports here on the top level, so let's module as top level test bench. Let's name what are the signals. So we have clock, we have reset, and we have 2 PWM output signals. Now top level, so this is top level is our device under test, and just assign the ports. Clock goes to clock, reset goes to reset. PWM out 1. What did I miss here? Add module. Oh, we add module. We are going to add in the add module. Okay. So over simulation, first initial begin. So clock starts from 0 level. So we're gonna first set the reset as 1, and then after 500 time units, which is 500 time units, and then we're gonna assign reset to 0. Okay, so now only left our clock. So clock is we define as same as PWM generation block, which is every the clock period is 5 nanosecond. So that means every 2.5 nanosecond the clock should be inverted. All right, our top level test bench is ready. Now let's run the simulation. But first, let me have a look. So we have PWM generation. So here duty cycle. Wait, PWM generation block. So here we have duty ratio as 0.5. So we should see 0.5 as a duty cycle of our PWM signal. The clock is 200 meg. Our PWM signal is 400 kilohertz. And then we're gonna delay the edge, which means over that time we defined as here 5, but here because the logic is subject 1, so the dead time should be 4 clock cycles between high side and the low side PWM signals. Let's run the simulation and have a look. Okay, let me bring the so we have the output, we have the port signals. Let me bring this original PWM signal, which is here internal signal. PWM gen out internal. Let me bring this signal so that we see the original PWM signal and then we see the complementary to PWM signals. All right, let me run for another 10 microsecond. Zoom fit. Now, so we first started reset as 1, so it's 1 after 500 unit time, and then it's gonna 0. So the actual PWM is actually the starting from here. And then this is the original PWM signal. Let's have a look if we zoom in here. So it looks like the duty cycle is 0.5. So it seems like the PWM block is good. Now let's look at this. Let's first validate its complementary signal, right? So this is the original signal PWM, and then it generated these two complementary signal, one high, one low, but between there's a dead time. So this is original signal. So it's gonna take 1 clock cycle to invert for the low side, and then from low side to high side. So boost stays low. This dead time is 1, 2, 3, 4 clock cycles, and then this high side will turn on. So this is from original PWM signal to the high side. It's gonna span over 5 clock cycles, but the dead time is 4 clock cycles. Now let's look at on the other side. On the other side, when the original PWM signals goes low, it take 1 clock cycles to the high side goes low, and then it's gonna take 4 clock cycles to turn on the low side. So it looks like our code works for the dead time. Now what I need to do here is let's have a look from the edge delay. Let's have a look. So the maximum is 6. It can goes up to 16 clock cycles. Let's say I want this dead time a little bit larger. Let's say 10. And then let's have a look, relaunch simulation. So 10 clock cycles, the dead time should be 9. So fit, let's have a look. So from here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So our dead time is now increased to 9 clock cycles. Now it should be the same as for the PWM go slow here. So it's gonna take 1, 2, 3, 4, 5, 6, 7, 8, 9. So it takes 9 clock cycles. So we increase the dead time now. It should work for let's see our original PWM signal. Let's see. I want to increase the PWM signal duty cycle to, let's say, 0.75. Launch. So as you can see, our PWM signal now duty ratio increased to 0.75. We didn't change the dead time from our previous compile. So here, so it take 1 clock cycle to inverter for the low side, and then it's gonna take 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 clock cycles for the dead time. Alright, so looks like our code works. So from here, now we can adjust the dead time in our PWM edge delay, whatever the dead time we can adjust from here. And then so if you want to increase more, if you want more dead cycles, that time, then we need to proportionally should increase this the counter. All right, so this is the end. Thank you very much for your attention. So if you have any questions or any thoughts about this code, please let me know in the comment section. Thank you. Peace.